Okay, we are back. This is our last example for connections, and this one we're going to be working backwards. So we've done several where we've been given a lot of information. We're asked to find stresses. This time we're going to go back and try to find this point load P. So we have a box beam fabricated from 2 plywood webs that are secured to dimension lumber boards at its top and bottom flanges. The lumber has an allowable bending stress of 1500 psi. The plywood has an allowable shear stress of 300. The 3/8-inch diameter bolts have an allowable shear stress of 6,000 psi, and they are spaced at intervals of 9 inches on center. The beam span is 15 feet. Support A can be assumed pin, C as a roller. Determine the maximum load P. So we were given lots of information. We were told that the lumber has a bending stress of 1500 psi, that the plywood has a shear stress allowable of 300, and we have an allowable shear stress for the bolts. So the things we'll need to check are we have lumber, we have an allowable stress, and we have to recognize that that is a normal stress because it's bending of 1500 psi. We have the plywood, and we are given an allowable shear stress of the plywood of 300 psi. And then we have the bolts, and our bolts, we are given an allowable shear stress of 6,000 psi. We're also told that they are spaced at 9 inches on center, so that means every 9 inches we're putting bolts into the side. The bolt itself has a diameter of 3/8 of an inch, and I went ahead and calculated that area for you. And the other thing I want to note is looking at the bolts is we are in double shear. Okay, so it's like we're doubling that area. So it is a double shear situation. Okay, so when we're looking at bending, I know that the if I were kind of to sketch out the bending, and we're just going to be looking at um, the bending stress of the lumber that's up here at the top, then I know with bending, it's straight. I see a positive moment, so I have compression top, tension bottom, and it's going to go this way. We don't have anything there, not there. So I have compression on the top, I have tension on the bottom, and they're going to be the same values because of the symmetry. So let's start with the lumber. So let's calculate our max load due to bending. And we know that with bending, MC over I. We can draw our shear moment diagrams based on this unknown force P. So if this is P symmetric, both of the reaction at A and C are going to be P divided by 2. My moment is the area under the shear. So I have length over 2 divided by P over 2, which gives me PL over 4. So my moment is in terms of PL divided by 4. C. C is that outermost fiber, and I have to understand that's where the largest normal stress develops. Okay, largest normal stress. So we are going to go up, and then we're going to continue up. So we are up 4 inches. If this is 16 inches, this is 8 inches to that point. So it's going to be 8 inches and then plus 4 to get to that outermost fiber. And then our moment of inertia is given and our allowable stress is given. So we have 1,500 pound per inch squared equals P L, 15 feet. So L equals 15 feet. PL, well, I need that in inches, so 12 inches per foot over 4, okay, times C, that's my distance to the outermost fiber, and it's symmetric, so it doesn't matter whether I go up or down, divided by I. And when I rearrange this, I'm going to have 1,500 times 3584 times 4 divided by 12, divided by 12, divided by 15. And I get that the maximum P due to bending is 9,956 pounds. So now I need to do the same thing, but we're going to find our max load due to shear in the plywood. And I have to understand that shear stress is VQ over IT. Again, I'm going to go back to my shear diagram, and I've done this in terms of that unknown P. So our shear is P over 2. I is given. Let's just go ahead and draw a little tiny half cross section here so we can label it easily. Okay, and there's our centroid. We are 8 inches up to this point, 4 inches up to the top. And if I know, I have to understand that maximum shear stress occurs at the centroid usually. Okay, so we're going to be coming down. We have a change in thickness. We have that jump, kind of come back around, change in thickness. That doesn't look symmetric, but we know that the maximum is going to occur right here with these wanting the plywood walls wanting to shear. So when I'm looking at this, my Q value, I have this area and this area plus this area. So let's start with these two legs. 2 times my area. Okay, these are a 1/2 inch, 1/2 inch, times height, 12. And then the centroid is going to be 12 divided by 2, so 6 inches. Plus, okay, plus this area here, and it is 3 inches, a base of 3, a height of 4. We have to walk up 8 inches just to get to that internal lumber. Plus, we have to walk up 2 inches, 4 over 2, to get to the centroid. So when I calculate this out, my Q is 192 inches cubed. So now we can go back and calculate that unknown P. So I was told that I have a shear stress of 300 pounds per inch squared equals V, well that's just P divided by 2, times Q over I, which was given 3584 inches to the 4th, and thickness 2 times 1/2 inch, 1/2 inch, so 2 times a 1/2 inch. I'm going to multiply 300 times 3584 times 2 times 1/2 times 2 divided by 192, and I get a value of 11,200 pounds. So this is the max based on that shear stress of the plywood. Now we need to do the same thing, but this time we need to do our max load based on bolts. Okay, and I know when I'm looking at bolts, we have to look at that shear flow, VQ over I, and we're going to recognize that Q is the strength of a fastener divided by spacing. And so we have strength of the fastener divided by spacing equals VQ over I. So let's go ahead again, and we need to figure out what is the force, the allowable force of our fastener. And I know that the allowable stress was given as 6,000 psi. And remember, when we have a bolt and it is fastened between something, we are trying to shear. Okay, we're trying to shear, and that's the force we're looking at. What is the strength? If the allowable shear stress is this, how do we find that allowable shear? Well, shear stress equals V over A. Okay, V over A. So V, which is the force of our fastener, the force of our fastener, equals shear stress times area. So the force of our fastener equals the allowable shear stress, 6,000 psi, times area, and I have that on the previous page, 0.110447 inches squared. And I need to remember that it is in 1-2 double shear. We've increased that capacity by increasing the shear planes. So when I come through here, I can find that the allowable force of a fastener is 1,325.364 pounds. So that is the force of one bolt. And now we've got to go back and figure out Q. So we're going to draw another little cross section here, and we're going to figure out what is our Q value, centroid. So our bolts are coming in sideways, okay? They are literally then attaching this piece of lumber. The area of this lumber, it is 3 inches by 4 inches. And then the centroid is going to go from the centroid of that lumber back down to the centroid of the hole. And we already calculated that it was 8 inches up. And then we're going to go up 2 inches because it's 4 divided by 2 to get to the centroid. So now we can put this all together. I have the force of a fastener, 1325.364 pounds. I have 1 bolt. I've already taken into account double shear when I found that capacity of the fastener, divided by spacing. Spacing was given back over here, 9 inches, equals, okay, V. This V is coming from our system. This is from our beam. This V was the shear force that would be the allowable shear force based on our bolt material, okay? So we have P divided by 2, that came off our shear diagram, Q, 4 times 3 times 8 plus 2, okay? VQ over I. I was also given as 3584 inches to the 4th. So I'm going to take 1325 times 1 divided by 9, my spacing, times 3584 times 2 divided by 12 times 10, which is 120, and I get a value of 8,796 pounds. And this is the maximum based on my bolt. So now we have to find the limiting value. And we have a P max from the normal stress, which came from that lumber at the top, and that value, so we have a P max, which came from the normal stress of the lumber, and that value was 9,956 pounds. We had a P max from the shear stress of our plywood, and that was 11,200 pounds. And then we had a P max, which came from the shear stress of our bolt, and that was 8,796 pounds. So the limiting or the maximum P that we could put on the system is 8,796 pounds. It is limited by the bolt capacity. So part 2 then said go back and calculate what your values were. So our bending stress in our lumber equals MC over I, and our moment was PL over 4, so I now have 8,796 pounds, length of 15 feet, 12 inches per foot, divided by 4, so that was my equation for my moment. I got it from my moment diagram. Moment diagram, PL over 4, okay? C, that was the distance all the way to the outermost fiber. So we had 8 inches plus 4 inches divided by the moment of inertia, 3584 inches to the 4th. So our normal stress in our lumber is 1,325 psi, which we know is less than yielding because we were not constrained by the bending stress. We were constrained by the bolts. Now we can find the shear stress of our plywood equals, not T, VQ over IT. Our shear force comes from P over 2. So I have 8,796 pounds divided by 2. Okay, divided by 2. That's my shear. Q, we found Q already. 192 inches cubed divided by moment of inertia, 3584. and then thicknesses. And remember, we found it was a 1/2 inch plus a 1/2 inch, 2 times a 1/2 inch, 2 times 1/2 inch. And our shear stress of the plywood equals 2,000, not 2,000, it's much smaller than that, 236 PSI. And again, that's less than our yield of 300 because we weren't limited by the plywood, we were limited by the bolts. So everything else is going to be less than. Box everything, that's the appropriate answer. And then our shear stress in our bolt is going to be 6,000 PSI because we designed to the limit of the bolt. And there you go. That's how you work backwards.